Okay, Riemann sums, part 2. Sorry we got interrupted in the last video. Had to go teach a virtual class. How exciting. Anyways, now let's go ahead and finish. We got just 2 more examples. Part ABC on that one, and then part A and B on the one on below. That's okay. Given the function y equals x squared plus 1, estimate the area bounded by that weirdly shaped graph and the x-axis from 0 to 2 by using a left Riemann sum, right Riemann sum, and then a trapezoidal Riemann sum. Alright, so let us go forth. I'm going to sketch the graph, and we're going to draw some rectangles from the left, then we'll do the rectangles from the right, then we'll do trapezoids. Alright, well that's a parabola shifted up 1 unit. So I know generally, let's see, 1, 2, 3, 4, 5, 6, 7, that's probably good. Shifted up 1, and then it's going to look more or less like this. It would have the left side too, but there's a pretty decent sketch. And then it wants from 0 to 2. I'm going to draw this very much not to scale. So how about we do, how about something like this? I guess we'll probably need it to be, there's 1, and then that'll be 1/2, and then 2. Okay, so we've got this region. Here's the area bounded by that parabola and the x-axis between 0 to 2. May not be to scale. In fact, it's almost certainly not to scale. That's okay. And let's take that region from 0 to 2. Let's split it into 4 intervals. Now, if the total width, right, the total width of that region is 2, that means I want my width for each one, right? If I take 2 and I split it into 4 regions, that means the width of each one is going to be 1/2. So my intervals are going to be 0 to 1/2, then 1/2 to 1, and then 1 to 3/2, 1.5, and then 3/2 to 2. Those are your 4 subintervals. 1, 2, 3, 4. And we would do rectangles from the left side of each of those, then we can do rectangles from the right, and then we can do the trapezoid. Let's do the rectangles from the left first. So my left Riemann sum, right, which is going to approximate the area. Remember, the area would exactly be the definite integration. We're going to approximate it with this Riemann sum. Okay, now let's see. If I have the 4 subintervals, the first one would be here, second one here, third, fourth. The universal width is going to be 1/2. So I'm just going to factor out that universal width. And then what I would need to do is if I draw, right, here's your subintervals. You'd have to draw the heights from the left on each side. So there we go, left side, left side, left side, and left side. It looks like this would be an under approximation, so you're going to be missing a little bit of area in each region. So that's okay, under approximation though. But for the first rectangle, I would need f of 0. I would need this y value on the left side of that interval is 0. So I would need f of 0, or we can use y of 0. I'm going to use f. Ooh, I guess I need parentheses. So I have the universal width, right? That's 1/2, that's 1/2, that's 1/2, that's 1/2. Since the widths of all 4 rectangles are 1/2, I have it factored out. Okay, the height of that first rectangle would be f of 0. Then the height of the second rectangle, here's 1/2, right? The second rectangle is from 1/2 to 1. You need f of 1/2. And then the third interval would be from 1 to 1.5, so you need f of 1. The left side of that third interval would be 1, so f of 1 is that height for the third rectangle. The last one is from 1.5 to 2, so I would need f of 1.5. Okay, so now you need to, right, I don't have to guess what these values are. It actually gives me the equation. So I could actually plug 0 into this equation, and then I can figure out what is that height. Well, if you plug in 0, you're going to get out 1. So the height of that first rectangle is 1. I don't know why I put a comma. Clearly need a plus sign. I could take 0.5 and I could plug it into the function. You don't have to guess what this y value is. You have the function, plug in 1/2 into the function, and then you would end up getting 1.25. I could take 1, plug it into the function to figure out what this third height of that third rectangle is. 1 plus 1 is going to be 2, so f of 1 is 2. And then if I took 1.5, plugged it into the function, that's going to tell me the height right here, which would be the height you would use for that fourth and final rectangle. So f of 3/2, if you plug it in, it would end up being 3.25. So we can approximate that area by doing a Riemann sum, split it up into little pieces, draw a little rectangle for each piece. And then let's see, if we were to calculate it, we would end up finding that here my area is going to be about 3.75. Again, I'll add all those heights up and then divide them by 2 or multiply by 1/2. And that would be an under approximation. Since the function's increasing, I know using the left side is always going to give you a little bit too little value. All right, now let's do the same thing, but let's do a right Riemann sum. So again, my integral, I could approximate by doing this Riemann sum from the right. So we're going to go ahead and get it. Now, the same subintervals are going to apply. So it's still 0 to 1/2, then 1/2 to 1, then 1/2, then 1 to 3/2, then 3/2 to 2. So the universal width is still going to be the same. What would be different is that for this first rectangle, instead of using f of 0 for the height, now I would use f of 1/2 for the height. Right? You would never use the leftmost number for the right Riemann sum, just like how for the left, I never used f of 2. But I'd use, let's do this one, I guess, in pen. I need to use f of 1/2 for the first one, then f of 1 for the second, then 1.5 would be the height for the third one, and then f of 2, right? So you can see now you have these 4 larger rectangles. Since your function's increasing, using the right side is always going to give you slightly too much area. Here we go. 0 wouldn't be the height of the first one. The first interval is 0 to 1/2. So I'd be using 1/2 for that first y value. Right here is the height for that first rectangle. Then your second interval is from 1/2 to 1. So I'd be using f of 1. Third is from 1 to 1.5. So I'd be using f of 1.5. And then the last region is from 1.5 to 2. So I'd be using f of 2. So whether it's left, right, or middle, that's going to tell you which x value do you use to plug in for the height. And then these numbers, we already had the f of 1/2, that was 1.25. F of 1 was 2. F of 3/2 was 3.25. And if you plug in 2 to the function, you're going to end up getting out 5. So then add all that stuff up, divide it by 2, or add all that up, multiply by 1/2. We're going to figure out that the area, if you use a right Riemann sum, is going to end up being 5.75. I didn't draw the graph, right? I kind of just did the same thing. I don't really want to do the graph again. So even for that last one, I'm not going to do it. The trapezoid, right? Here, if you sketched it, you'd have the slanted top, slanted top, slanted top, slanted top. So it's going to be a much better approximation because that line is slanted. It hugs the graph a lot closer than the flat across rectangle, either from the left or from the right. The trapezoid is generally the best. Okay, now let's do it. Still the same 4 intervals. So let's do my trapezoid. Area would be the integration from 0 to 2, which we're going to approximate with a trapezoidal Riemann sum. Now remember the area formula of a trapezoid is 1/2 width and then base 1 plus base 2. I'm going to factor out the 1/2. And then all of those intervals did have the same universal width. So I'm going to factor out the universal width, which was also 1/2. Remember, if the total width was 2 and you split it into 4 pieces, then the width of each one would be 1/2. We did that in part A and in part B. So I have the 1/2 from the formula factored out. I have the universal width factored out. Now I need to figure out which y values you're going to use. You'd use this side once. You'd use this value twice, right? Because that would be the right side of the first trapezoid. Then it would be the left of the second. So this y value is going to use twice. That one would be used twice. That one would be used twice. So 3 of the y values get used twice, once, and then that one once. So here we go. F of 0 gets used once, plus 2 times f of 1/2, f of 1, f of 3/2. Those all get used twice. So 1/2, 1, and 3/2. Those get used twice. And then the last one, f of 2, I guess we should put u. That's kind of a little bit confusing, right? That gets used once. That all get used twice. And then that one gets used once. So plus f of 2. So I have the 1/2 from the formula factored out. Then I have the universal width also factored out. If you don't want to do that, you could always just do each trapezoid individually, right? 1/2 base 1 plus base 2, divided by, and then times the width. Then 1/2 base 1 plus base 2, then times the width. Then 1/2 base 1 plus base 2. You could always go through and do it individually if you like. This way is just a little bit faster. The left side you only use once. The right side you only use once. But the values in the middle, here you're going to use them twice. You add the ones in the middle, multiply it by 2. All right, 1/2 times 1/2 is 1/4. F of 0 was 1. And then this one, f of 1/2, was 1.25. F of 1 was 2. Then that was 3.25. And then f of 2, I think, was 5. So the left height, the right height used once. All those heights in the middle you got used twice. And then here we can end up figuring out that trapezoidal area is 4.75. Now, did you really need to do all that work? No. Remember, we did the left with 4, and we did the right with 4. And it's asking us for the trapezoidal with those same 4, right? Those intervals never changed. So I could have just taken the left and taken the right. And if I would have averaged those two, you would have gotten the trapezoidal. And yes, I would be perfectly okay if you have a question like this. If part A and B have you do the left and the right, and then later on, part C or whatever, part Z, later on, if you've already done the left and the right, then yes, it's perfectly okay to just average them to get the trapezoidal. But you need to make sure that it's the same subintervals. If that was any other number besides 4, then you would not be able to average the left and the right. Or if one of those was different, if one of them was 4 and the other one was 3, or if one was 4 and one was 8, it wouldn't work. But if all three, if the left and the right are the same subintervals, and then you want the trapezoidal with the same exact subintervals, then yes, you could just average the left and the right to get the trapezoid. Okay, last one for today. Here we go. We got water flowing into a tank over a 12-hour period. The rate at which water is flowing into the tank at various times is measured, and the results are given in the table below, where R sub t is measured in gallons per hour, and t is measured in hours. It tells me the tank contains 150 gallons of water when time equals 0. Okay, and it says it looks like at time equals 0, there's 8. The flow was 8 gallons an hour. When time equals 5, the flow was 8.8 gallons per hour. And then when time was 8, 9.3 gallons per hour, and then 12 hours was 9.2. So I have all these rate flows at these specific times, and then it somehow wants me to tell how much water was in the tank after those 12 hours. Well, this kind of gives us the first chance to kind of hit upon a really big conceptual understanding that hopefully you will get into your brain. The integral of a rate of change is the amount of change. That's what integration does. It accumulates all those little momentary values. Like when you're integrating and you're getting the area, what you're getting is all these little values for all those really, really, really tiny, thin rectangles. Eventually, next time, we're going to see those rectangles become infinitely thin. But when I accumulate all those little lines, and when I compile all of those little tiny areas of those really narrow rectangles together, when I accumulate them, it's going to give you the much larger, more significant area of the region. Or here, when I have this rate function, if it models in gallons per hour, when I accumulate all of those instantaneous values, right, over these 12 hours, if I accumulate all of those little gallons per hour over the course of 12 hours, right, gallons per hour times your 12 hours, then the units tell us that's just going to give you gallons. So when you integrate, what you're doing is you're accumulating all of the change. The derivative is the instantaneous rate of change, and when you integrate it, it's going to accumulate. How much change have we gone through? How much change has there been? The integral of the rate is your amount of change, or the integral of your rate of change is your amount of change. So if I want to know how many gallons have come into the tank, you'd have to integrate the rate flow function. Okay, so let's go forth. Part A. Estimate the number of gallons of water in the tank at the end of the 12 hours by using the left Riemann sum. 3 subintervals and values from the table. It's always going to tell you what Riemann and how many. It's always going to tell you what to do. And of course, show the work. So here we go. The change in the water. In order to get the change in the water, that would be my integration. If I want to know how much water flows into the tank from time equals 0 to time equals 12, you would have to integrate the inflow function from time equals 0 to time equals 12. That integration is going to accumulate all of those momentary values from time equals 0 to time equals 12. It's going to accumulate them, compile them together, and then when I do that, it's going to give you your amount of change. So the amount of change is the integration, which we are going to approximate by doing a Riemann sum. Now let's check it out. 3 subintervals. So the first one's going to be 0 to 5. Second one's going to be 5 to 8. Third one is going to be 8 to 12. Do we have universal width? The first one is going to have a width of 5. 5 minus 0 is 5. The second rectangle is going to have a width of 3. So right away, you know there's not going to be universal width. So we're just going to have to do each shape individually. So let's go for it. First rectangle, right, it's from this interval 0 to 5. The width would be 5. And then since we're doing a left Riemann sum, you'd use the x value on the left and its corresponding y value. You would use 8 for the height. Okay, the next interval would be from 5 to 8. The width, the change in the x in that interval would be 3. And then since we're doing a left Riemann sum, you would use 8.8 for the height of that second rectangle. And then the third region would be from 8 to 12, which has a width of 4. And then for that third rectangle, you'd be using the left height for the value. Okay, sorry, I had to help a student really quick. Let's get back into it. So we had the 3 different rectangles. The first one with the 5 using the left side. Second one with the 3 using the left side. And then we had the third one using the left side, right? So we have that 3 region, those 3 rectangles from the 3 regions. Let's get all that together. When I calculate this up, you should get 103.6 in the units for that accumulation, right? That change in water. If you were to take your accumulation of gallons per hour over the course of 12 hours, what that would tell you is the amount of gallons that has come into the tank over those 12 hours. Now, you have to be careful. Sometimes you will have questions that ask how much water flows into the tank over 12 hours. And if you had a question that asked something like that, purely what is the amount of change, how much comes in over that time interval, then 103.6 would be the answer. But that is not what this question says. It doesn't say how much comes in. It says how much is in there at the end, right? It says estimate the number of gallons of water in the tank at the end of 12 hours by using this Riemann sum. So this is just the amount of change. That's how much water flowed in. What you have to now do is take this value and add it to how much was originally in there, right? If you have an inflow function, you would take your initial amount and then you would add your amount of change. Or if you had an outflow function, you would take your change and you would subtract it from your initial. But if it just wants the change, yeah, that just is the integral. The integration of the rate is going to give you the amount of change. But if it wants the final quantity, if it wants the final amount, then you either take your initial and add to it, or you take your initial and subtract from it. So let's add 150. And I'm going to get 253.6 gallons. That's how much water is in the tank at the end of 12 hours, right? That's at 12 hours. You started with 150. This is how much comes in. So that's how much is in there at the end. Okay, now let's do the same thing, but we'll use a right Riemann sum, and then we'll be done. Remember, the change in water is the integration. But we're going to approximate that integration by doing a Riemann sum. The intervals aren't going to change. It's still going to be a width of 5, then a width of 3, then a width of 4. So those widths are the same. What is going to change is the values you use for the height for each region. Okay, so let's think. The first one would be 0 to 5. That's my interval. For the left Riemann sum, we used 8. But now for the right Riemann sum, we're going to use 8.8. Next region, 5 to 8. The width is still 3. But instead of using the 8.8, which is what we did for the left, Now I'm going to use the 9.3. Everything just kind of gets bumped over, right? Now we're not going to use 8. That shifts over, and that'll end up coming down here. So the second region, you'd be using the right value, 9.3 for the height. And then for the third region, you'd be using the 9.2 for the height. So if you just focus on one rectangle at a time or one trapezoid at a time, these Riemann sums should always be pretty okay. Anyways, when you calculate that up, it ends up being 108.7 gallons. And then it says, estimate the number of gallons in the tank at the end. So again, we'd have to take that, add the 150, and I would get 258.7 gallons. That's how much is in the tank at the end of 12 hours, right? That's at t equals 12 hours. So be careful. If I have to ask, or if you have to answer purely how much change happened, how much came in or how much went out, then all you need is the integration value itself. But if it asks for how much that final quantity is, you take the change and you either add it to what you started with or you subtract it from what you started with. Sometimes you'll get questions that ask for the change. Sometimes you get questions that ask for the final quantity. Should be pretty okay. Now let's talk about just one more thing, just quickly, right before we kind of wrap up this stuff with the Riemanns. Right? If you're given the table and you're asked to do a Riemann, right, and then telling me what the final area is, like that should be okay. But what if instead of giving you the completed table and then asking for the area, what if it said, like, hey, like this is going to be missing? What if it says this is some constant? What if that's k? But then what if it tells you the area? Like what if it says, hey, that integration, that left Riemann sum is going to be 103.6. If you set it up, if it tells you what the total is, and if one of the pieces was missing, could you set it up and then solve for what the missing piece is? Yeah, like if you did that, you would end up getting that the k is 8.8. So just be careful. Sometimes all the pieces in the table may not be there, right? But if one of the pieces is missing, but you're given the total, you kind of just set up your equation, and then you can just work backwards and you can solve for what that missing piece would have been. That's a really common extension type of a question. I think those are harder, but those are very doable, right? So hopefully that makes sense.